Hello, everyone. Welcome to today's webinar. We're so glad to have you here. We're going to be getting started with the presentation in just a few minutes. But before we get started, I do want to tell you about some other upcoming webinars that we have going on here at the center and in collaboration with our partners. On Wednesday, November 20th, we will have a presentation on ergonomics and your parents, musculoskeletal challenges of home healthcare for a loved one. And that will be with the Defense Centers for Public Health's perspective. And that's with Kelsey Makowski, MS, CPE, and John Petkins, MS, CPE, and PhD, and the John Hopkins Education and Research Center for Occupational Safety and Health. And on Wednesday, December 4th, we'll have a presentation on climate change and environmental degradation impacts on worker well-being. And that will be with Gina Solomon, MD, MPH, and the California Labor Lab. Our next industrial hygiene webinar is going to be on Tuesday, December 10th, on general population performance in passing a fit test for N95 respirators. And that will be with Majid Bajeri Hosanabani, a PhD candidate, and the Midwest Center for Occupational Health and Safety Education and Research Center. So for more, you can visit us online at cueh@berkeley.edu/webinars. And I'll go ahead and put that link in the chat. And on behalf of education and research centers throughout the country, it is my absolute pleasure to welcome you to our Industrial Hygiene Series. This is a collaborative effort on behalf of each ERC's continuing education program and aspires to provide access to current research supported through NIASH ERC programs. Thank you so much for joining us today. Today's webinar, Optimizing Calibration Methods for Low-Cost PM2.5 Sensors in High-Concentration Occupational Environments, is presented by PhD candidate Runcheng and the Rocky Mountain Center for Occupational and Environmental Health. A few housekeeping items first. You are going to be muted during this presentation. If you'd like to ask a question, please enter it into the online Q&A box. And we'll save time at the end of the presentation to address as many questions as possible. We'll also have the chat open, so feel free to use it to participate and join in on the conversation. And this presentation is being recorded and will be made available on the Center for Occupational and Environmental Health YouTube page within 5 business days. All participants who logged in with their registration email for the full live presentation today will receive an email tomorrow with a link to an evaluation form that will qualify you for a certificate of completion with 1 continuing education contact hour. Once the evaluation is completed, you'll be able to access and print your certificate. That concludes our housekeeping announcements. And without further ado, it's my absolute pleasure to welcome our speaker for today. Thank you so much for joining us. We're joined by PhD candidate Runcheng. She is in industrial hygiene program at the University of Utah, specializing in air quality monitoring and sensor calibration. Her research focuses on improving the accuracy of low-cost PM2.5 sensors using machine learning and environmental assessments. She has extensive experience in exposure assessment and environmental toxicology, contributing to projects such as the Environmental Influences on Child Health Outcomes, or ECHO, and UCOVER, UCOVER. She has presented her work at national conferences and received multiple scholarships for her contributions to industrial hygiene and occupational health research. And it is our absolute pleasure to have her here with us today. Thank you so much for joining us. We're looking forward to your presentation.
Okay, thank you. I'm going to share my screen, and after that, I think we can start our presentation. Give me 1 moment. All right, can everyone see my screen?
Yep, you're good to go. Thank you.
Yeah, so my name is Runcheng Fang, a PhD candidate from University of Utah, and I'm really happy to share my research with you guys today. And today's topic is optimizing calibration methods for low-cost PM2.5 sensors in high-concentration occupational environment. And that is a comparative analysis of 3 different models, which are linear regression, random forest, and polynomial regression models. So before the study begin, I want to introduce a little bit about myself. I am a PhD candidate in industrial hygiene from University of Utah, and before that, I got my master from University of Cincinnati. And I got my joint bachelor degree in public health and safety engineering from 2 different schools. And my research interests including the air quality monitoring, occupational health, and exposure science, environmental epidemiology, and the sensor technology. So let's start with some background. Firstly, we are talking about PM2.5. So we all know PM2.5 is a significant air pollutants, primarily linked to urbanization and industry activities. And the occupational environments often have a higher concentration, putting the workers at greater risks. So exposure to PM2.5 can lead to several chronic health conditions and notable issues including respiratory disease like asthma and COPD. And it also induces the cardiovascular disease due to the prolonged exposure. And the increased risk of lung cancers, and particularly in the high exposure environment. So to reduce these health risks, accurate PM2.5 monitoring is crucial. It ensuring the regulatory compliance for the air quality standards, and it also help minimize the health risks for the workers who by providing the data to implement the safety measures. So the effective monitoring and mitigation strategy are essential to safeguard the health, particularly for the workers in the industry where the PM2.5 exposure is serious. So why do we need to monitor the PM2.5? Let's start begin with some health risks. Like I just said, PM2.5 particles are known to cause various health issues, particularly affecting the respiratory and cardiovascular health, like some disease I just mentioned. And in terms of occupational sightings, first of all, the workers in the environment with high PM2.5 exposure, such as the factories and the construction sites, are heightened risk. Besides, prolonged exposure in this high PM environment can lead to serious health effects, including reduced lung functions, respiratory issues, and the cardiovascular problem. So this risk make PM2.5 monitoring essential in such sightings to ensure worker health and safety. And I also want to mention the importance of calibration. The accurate air quality data is crucial for assessing exposure risk and ensuring regulatory compliance in occupational health. And to achieve the accurate data, the sensor must be properly calibrated, because uncalibrated or poorly calibrated sensor can lead to inaccurate readings and like underestimating or overestimating. And only the well-calibrated sensors can provide more reliable monitoring, which is essential for protecting workers' health and maintaining the compliance with the safety standards. Now, I want to talk a little bit about the low-cost sensor. What is low-cost sensor? Low-cost sensor are compact, affordable device used for monitoring the air quality. They provide a cost-effective solution for detecting pollutants, such as particulate matters. So in these studies, we use the Plant Tower PMS 3003 sensors, which is a popular low-cost sensor that detects PM2.5, PM10, and PM1. And it's using the laser scattering technology. And the reason we use that because it is known for effective in the real world environment, making it suitable for both research and practical applications. And what are the applications of the low-cost sensor? Firstly, it can be used as personal monitoring for the individual to track the exposure levels. And as a community side, it can be used as community-based monitoring to raise awareness and promote collective actions. And to the research projects, due to the local sensor, their accessibilities and enabling to large-scale air quality studies that might be expensive with traditional monitoring equipment. And the monitor we use in this study is called AirU. And what is AirU? AirU is a air quality monitor, which is to make which is a device that can deploy into homes or anywhere you want. We add a board to the plant tower sensor, which used to store the data. Then put this system into a case, it becomes the ARU. So ARU is not just a sensor anymore. It's a smart device that gives us real-time information about the air quality. It doesn't just measure the particles. It also tells us about the temperatures and humidity when it's working. So before I do the sensor technology studies, I actually think the sensor and the monitor are same things, but actually they are not the same stuff. So the sensor is a device that detects and measures a specific physical quantity, like particle matters, temperatures, humidity, or gas concentration. It converts the detected information into a signal that can be interpreted or processed. So the example of the sensor, including the low-cost PM2.5 sensor, like the plant tower sensor we use in these studies, the temperature sensors, or the gas sensors. However, a monitor is a more comprehensive device that uses one or more sensors to provide the readable environmental data. It often includes additional components such as the power supply, data processing units, and a display to show the output. The example of the monitors, including the dust track aerosol monitor and the ARU air quality monitors we use in this study. So, what local sensor provide us with the essential air quality data. The accuracy and the reliability of this data depends heavily on the calibration. So let's explore the different calibration methods and the challenge we face with. The first I want to talk about is the calibration approaches. Calibration can be conducted in controlled lab environment or directly in the field, each offering the benefit and drawbacks. The lab calibration ensuring the precision under the stable conditions, while as the field calibration reflects the real-world variabilities. And the techniques used nowadays almost the linear regression or the machine learning models. The linear model is most people used in the past because it is simple and more transparent, and it is easier to use and interpret. However, the machine learning is a modern technology and really a hot topic in recent years. And there are many research demonstrate that machine learning makes a great job applied in local sensor calibration. So because the machine learning model is a complex model, like random forest can handle non-linearity and the interaction within the data. And there is a table I got from a review paper, list the good and the bad side of the machine learning and linear regression model applied in sensor calibration. Both of them hold something we needed and something we do not want. However, the calibration is not without its challenge. The first come into my mind is time consumptions, especially calibrating large numbers of the sensors individually is really a labor intensive and time consuming for the big projects. So one of our projects need to calibrate like 300 more sensors, which is like 1,000 years work. Moreover, the ever-changing environmental conditions can make maintaining calibration accuracy a continually challenge. So come to the ever-changing environment, local sensor often faced with accuracy issues, especially in high concentration environments. The sensor response can become non-linear and lead to inaccuracy. This can result in either underestimating or overestimating exposure rates. Environmental factors like temperature, humidity, and the duration of exposure can affect the sensor readings. These factors may cause the sensor's accuracy to drift over time, leading to incorrect measurement. So to maintain the accuracy, frequent recalibration is needed, especially as the conditions change. And the previous studies have demonstrated that the high humidity levels and extended deployment duration significantly impact the sensor calibration accuracy. These findings underscore the need for developing calibration methods that can adapt to these factors, ensuring the reliable data over extended period. So in summary, these challenges highlight the complex of calibration low-cost sensor in high concentrations and the variable environment. So addressing these issues is critical to improve the data's accuracy, which is essential for effective exposure risk assessment. So come to our studies. Their 3 listed studies are all a part of one overarching project aimed to optimizing calibration methods for the low-cost PM2.5 sensors, especially in different concentration environments. The studies are as follows. The first one is optimizing the air quality. The first one is optimizing the air quality monitoring, a comparative analysis of linear regression and machine learning techniques in laboratory calibration of low-cost sensors. This one is aimed to simplify the process of the calibration, which saves a lot of time when doing large longitudinal environmental or occupational epidemiology studies. And then the second one is explore the effect of temperature, humidity, and deployment duration on sensors performance in indoor environment. These works help us understand the sensor drift and calibration accuracy. And the current study, which the one I'm going to talk about today, is focused on optimizing calibration methods, specifically in high concentration occupational environment by comparing different calibration models. And the reason we did a lot of studies about that, because we want to improve the calibration methods for local sensors. We think it's crucial to enhance the reliability of this device, particularly in high concentration occupational environments. So this research aims to address the challenges and optimize the calibration approaches. And the goal of this research is to evaluate the performance of 3 different calibration models: linear regression, random forest, and polynomial regression for low-cost sensor in the high concentration PM2.5 environment. And the aim is to identify the best calibration approaches for the accurately measuring air qualities in these challenging conditions. And now we come to the methods. Firstly, we will talk about the experiment setup. We are specifically focusing on the plant tower sensors and comparing them to a well-known air quality monitor, the dust track, which we used as our reference device. Now let's talk about where all this happens. The calibration chamber. Calibration chamber is a special space we built for control the environment conditions very precisely. Why we need this? Because to test our sensor accurately, we need to make sure we can replicate the same conditions over and over again. Here are some pictures of our calibration chamber. And in these studies, we are using 8 brand new plant tower sensors. We place them together with dust track reference device, named the sensor from sensor 187 to sensor 183. And all low-cost and dust track sensors record the PM2.5 levels at the same time intervals. And we start by selecting ammonium nitrate to create the particles to simulate the real-world conditions as closely as possible in the lab. And for our initial setup, we focus on maintaining a clean and dry airflow within our calibration chamber. And we turn on all the sensors and dust track at the same time to start, and turn them off together at the end of the test. This makes sure they all work under the same conditions. And we carefully control the level of the particles in the air, increase the concentration step by step from the 0 to 1,000 microgram per cubic meter. And we allow each level to stabilize for 10 minutes to ensure our measurement would be consistent and reliable. And finally, for the data collection, we record the data at the stable intervals to ensure our accuracy. And if we saw any abnormal change or spike in the data, we would adjust the setup and repeat the part of the test. It's all about the precision and making sure the data reflect the sensor. This sensor was faced in the real world. And then now I'm going to explain how we prepare and analyze the data to make sure our findings are accurate and meaningful. First, we clean up the data. This means removing any missing values and outliers. These are the data which much different from each other. We also adjust the readings from the depth check using a correction factor of 1.78 because we use ammonium nitrate. And next, we move to the calibration modeling. We use 3 different models applied in our data set. They are linear regression, polynomial regression, and random forest. And to evaluate the calibration models, the following matrix we will use. They are R-square, MAE, PE, and MSE. And come to why we choose these 3 specific models in our studies. This slide explains why. Mostly, we choose these 3 models mostly supported by literatures, which demonstrate these 3 models, their effectiveness. First is linear regression, which is a straightforward and efficient model. Can captures linear relationship in sensor data, and it serves as foundational reference for comparing with more complex models, giving us a simple start point. The study like Sayahi and Pike's study have widely validated like linear regression for the basic sensor calibration is successful. And with the polynomial regression, we introduce a higher order term to capture the non-linear sensors behavior. This model is a step up in complexity from the linear regressions, providing a balance with all the computational demands of sensible models. Lastly is random forest. Random forest excels at handling complex non-linearity relationship by combining multiple decision trees, which minimize the overfitting and handle noise effectively, and making it stable in fluctuating conditions. Studies like Wang and Zimmerman have shown that random forest can significantly improve the sensor performance and calibration accuracy. So let me be specific about these models. I also save time for linear regression because I believe everyone understands what it is. So I'm going to introduce a polynomial first. The polynomial regression is a type of the regression analysis that models the relationship between the independent and the dependent variables using polynomial terms. Unlike linear regression, which fits a straight line, polynomial regression fits a curve, allowing it to capture non-linear relationship in the data. This flexibility makes it useful in the situation where the data patterns are not linear. And now let's define some key terms related to polynomial regression. The first is intercept. This is the start point of our curve when all other terms are 0. It sets the baseline for the model's predictions, which is the same to the linear regression. And the coefficients are the weights applied to each polynomial term. They help adjust the fit of the curve to capture the patterns in the data. The higher order coefficients allow us to better capture the nonlinearity variations. In this study, we'll use 3 order to model the data. And why we use the polynomial in our studies? Because it's particularly useful for the data where the relationship isn't a straight line. And by adding the polynomial terms, we can create a more flexible curve that adapt to the complex variation in the data. Yeah, let's talk about the random forest. Random forest is a machine learning technique that uses a collection of decision trees to make accurate predictions. So imagine each tree has a separate decision-making tools, and the random forest model combines these tools and taking an average of their predictions to give us a more reliable result. This approach is particularly useful in handling complex data sets, like the air pollutant data we work with. And let's go over some key terms to understand how random forest work. The first is importance. Importance is a term indicates how much each sensor feature contributes to the model's prediction. The higher importance means the sensor is playing a larger role in estimating PM2.5 levels. This study only focused on the readings on the local sensor and the reference device, so all the importance were one. And to come to the mean prediction, this is the average predicted PM2.5 level for each sensor, and it essentially tells us how the model expects each sensor to respond in terms of the PM2.5 sensors based on the data patterns it has learned. And the reason we choose random forest for few important reasons. Firstly, random forest is great at managing complex sensor data, especially when the relationship are different in different concentration. And the second is by averaging the result from multiple trains, random forest provide a more accurate and balanced prediction. And also, there are a lot of research evidence that random forest doing well when it comes to the local sensor calibration. So in our initial analysis, we want to explore the relationship between the sensor and the sensor readings and the reference across the entire data set. This approach is aimed to evaluate the performance of 3 different calibration models across a wide range of PM2.5 concentrations from the low to high level. And we also did a breakpoint analysis. There are 3 segments were defined based on the PM2.5 concentrations. There are segment A, which including 0 to 150 microgram per meter. Segment B is 150 to 347 microgram per meter. And segment C is greater than 347. The reason we're doing that is to determine the best calibration model for each concentration range to ensure the accurate measurements. But why do we choose these breakpoints? There are 2 breakpoints were identified in this study. The first is 150. We choose that based on literature. We use the same data set from our studies, and this research demonstrated that the sensor's response begin deviating from the linearity beyond this concentration. And the reason we choose 347 this point is because we run a data analysis determined through the statistical analysis of the sensor's data to minimize the combined mean squared error, which is MSE. And the purpose of this breakpoint is to understand the sensor behavior across the different PM2.5 concentration range and select the most suitable calibration model for each segment. And let's take a look about the result. Let's take a look of the no breakpoint analysis first. So from the table, we can see the random forest outperforms linear regression, the polynomial regression in accuracy, reliability, and robustness across all the metrics, making it most effective calibration model for these sensors. And the linear regression performance less accurately, especially in the sensor with the higher errors. This may be more suitable for a single low exposure environment where the high accuracy isn't critical. And polynomial regression performs moderately well. It's better than linear regression, but not as effectively as random forest. It may be an option when a balance between the simplicity and some level of nonlinear calibration is needed. But it falls short in complex high concentration scenario. Now we're taking a look at the breakpoint analysis. First, we'll take a look about the linear regression. So at the segment A, the sensor exhibits strong linear response in this range with a slope close to 1 and a minimal intercept. This indicates that the sensor accurately measures the PM2.5 concentration at the lower levels. For instance, the sensor 187 has a slope of 1.04 and an intercept of minus 1.87, suggesting a reliable linear relationship. And at the segment B, as the PM2.5 concentration increased, the slope of the linear models vary more widely. The sensors show a notable deviation from the perfect linearity. For example, the sensor 187 has a slope of 1.35 and the intercept of minus 41, indicate a substantial change in the sensor behavior compared to the segment A. And at a higher concentration, when it comes to segment C, sensors exhibit significantly deviations from the linearity. It means it needs a more complex model, same as the sensor like 187. We can see at the segment C, it shows a slope of 2 and intercept of minus 275, which indicates nonlinear behavior at these concentration levels. And let's take a look at the random forest analysis. In the segment A, the mean prediction values range from the positive to negative, which indicates the variabilities in the sensor response at the lower concentrations. And when it comes to the segment B, the mean prediction values are higher, reflecting a different tendency or behavior as concentration increased. When it comes to the segment C, the mean prediction values are significantly higher compared to the A and B, which suggests that the sensors are predicting much higher PM2.5 levels in this range, likely corresponding to higher actual PM2.5 concentrations. And lastly is polynomial regression analysis. So in this analysis, we can see at the segment A, the intercept and the coefficients are relatively small, indicate a simple response. And when it comes to the segment B, the intercepts are negative and the coefficients are larger compared to the segment A. This indicates a needed for strong correlation, which may be due to a transition in sensor behavior. And when it comes to the segment C, the intercept values are even more negative and the coefficients are higher, reflecting a more complex correlations needed at the high PM2.5 concentrations, where sensors nonlinearity is more pronounced. So this table provides a comprehensive of 3 calibration models across several sensors and segments. Each row represents a performance matrix for a specific model on a particular sensor in one of 3 segments, where each segment corresponds to different PM2.5 concentration levels. That is a big table with a lot of information, but through the table, we can find out in the segment A, the linear regression performance reasonable well with low MAE and MSE values. However, the random forest outperforms it slightly, especially in the terms of lower MAE and PE, which is essential for our fine-grained predictions. As we move to the segment B, the polynomial regression starts to show improved performance over the linear regression due to its ability to capture the nonlinear patterns. And the random forest still holds the edge, offering the best balance of the MAEP and the MSE. And segment C is the most challenging due to the high PM2.5 concentrations. Here, the linear regression struggle with the high MAE and MSE, whereas the polynomial regression improves. However, the random forest demonstrates the best performance, effectively handle the nonlinear and high variance data. In conclusion, random forest consistently provides the lowest errors and the highest R-squares values especially in high concentration environment, where the linear and the polynomial models show the limited. And here we are compare the performance of 3 models across different concentration segments more specifically. So from that, we can see in the segment A, where the PM2.5 concentration are lower, linear regression performance reasonable well with the MAE of 2.5 microgram per cubic meter, and the R-square value of 0.98 indicates a strong fit. And random forest at this range outperforms linear regression with a MAE of 1.2 microgram per cubic meter and R-square of 0.99, showing the excellent predictive accuracy in this range. But personally, I don't think it's too much different compared to the linear regression. And come to the polynomial regression, which offers a similar performance to the linear regression with a slightly better MAE of 2.4. However, it doesn't outperform the random forest. And moving to the segment B, which includes the moderate PM2.5 levels. Linear regression begins to lose accuracy with the MAE increased to the 5.6, indicates its limitation with nonlinear data. And the random forest maintains strong performance with a MAE of 2.4 microgram per cubic meter, and the R-square still at 0.99. It captures the non-linear patterns more effectively in this range. And polynomial regression improve upon the linear regression with a MAE of 4.5 microgram per cubic meter, providing moderate levels of accuracy that places between the linear regression and the random forest. And when it comes to the high concentration range of the segment C, the linear regression struggle significantly with a MAE of 12 and the R-square of 0.94, indicate a poor fit for high concentration levels. And the random forest remain robust with a MAE of 3.8 and the R-square of 0.99, showing that it can handle complex and high variance data effectively. And polynomial regression performance better than linear with the MAE of 6, but still doesn't match the performance of random forest in this challenging segment. So by comparing above, we can see the sensor response varies among the different segments. In segment A, the sensor response is generally linear, meaning a simple linear model might be sufficient for calibration. This segment represents low to moderate exposure levels, where the linear regression and other simple models tend to perform well. And when it comes to the segment B, this range is the transition zone where the sensor behavior starts to become nonlinear. This shift from the linear to nonlinear response make it more challenging for linear model to maintain the accuracy. And this segment is crucial for testing and adaptability of more complex model like random forest and polynomial regression. And finally, to the segment C, here the sensor's response is fully nonlinear, which means the traditional linear model struggle to capture the data patterns accurately. The high concentration range demonstrates the needed for the robust, flexible models like random forest to handle the increased complexity and the variability in sensors response. Let's take a look about our discussion part. So the linear regression is effectively for initial calibration at a lower PM2.5 concentration, such as those in the segment A. And however, it exhibits significant limitation as the concentration increased. And at the higher concentrations, especially in segment B and C, linear regression struggle to capture the non-linear patterns in the data, leading to a higher errors. This makes it less suitable for the complex real-world environment where PM2.5 levels may vary significantly. And random forest stands out due to its robust performance across both linear and nonlinear regions. it effectively handles complex sensor behavior and the interactions between the multiple features, which make it highly suitable for high concentration environments. And the model flexibility and robustness allow it to provide a more accurate prediction across all the segments, also performing the other models in both low and high concentration levels. And polynomial regression serves as a middle ground solutions. It captures some non-linear patterns better than the linear regression, and offering a moderate improvement in accuracy, particularly in higher concentration segments. However, it still lacks the robustness and the adaptability of random forest, which makes random forest a more reliable choice overall for handle the diverse and high variance data. So come to the model selection problem, which model we should choose. And I think we need to think about a couple balance question here. The first balance is which model I should choose, machine learning model or the linear regression model. We know the machine learning model provide a better prediction result, but the linear regression is not bad. So here is the question: how good is good? How accurate is accurate? What is acceptable errors for the local sensor? Actually, I did not find any reference for these questions, but from the result we have from this research, 1.3 micron per cubic meter difference from the random forest and linear regression at the low concentration levels, which I don't think we needed to use any machine learning model. And it also depends on the scenario we needed. If we want to use a local sensor at a really high exposure environment, like over 350 micron per cubic meters environment, we can just go ahead and use random forest because it have a remarkable better performance. But if for the daily monitoring, I think the linear regression is fine. But everything I said now is just my own opinions and the result I found from my studies. As I said, we do not have a golden standard to determine the accuracy. Then it is the flexibilities. I believe everyone understands the linear regression, but not all of people in our field understand the machine learning. And I think we cannot make things complex if we can solve the problem in a simple way. And I think that is the open question for all professionals here today may need to think about what is the standard for us to give a definition of the accuracy of the local sensor. And this slide highlights the key contribution of our study, focusing on its impact on occupational health and the importance of selecting appropriate calibration models for the PM2.5 monitoring. The first, let's talk about the occupational health impact. So we all know the high PM2.5 concentration commonly found in industry settings posing significant health risk to the workers exposed to over long period. And our study emphasized the need for the robustness calibration methods to ensure the accurate monitoring of PM2.5 in this environment. Without accurate calibration, the PM2.5 measurement may underestimate exposure, leading to not enough protection measures for the workers. Next, the selection of the calibration models. Our findings highlight that the different occupational and the industry settings have a unique challenge and demands when it comes to the PM2.5 monitoring. And now these studies underscore the need for tailored calibration models that can adapt to specific environmental conditions and the concentration levels, ensuring the reliable data across a wide range of the scenario. By understanding the strengths and the limitation of each model, we can make informed choice that enhance the accuracy of PM2.5 monitoring, ultimately supporting better health outcome in the workplace. In summary, our study contributes to both occupational health by advocating for more accurate PM2.5 monitoring and to the broader field of the sensor calibration by demonstrating the importance of the sensor, the model selection. This work provides a foundation for future studies, which aim to improving air quality monitoring in various occupational settings. And this slide covers the limitation of our current studies and outlines the potential directions for future research to address these limitations and expanded our findings. So starting with the study limitations, our calibration tests were conducted in controlled environment, which may not fully capture the variabilities presented in real-world occupational settings. The factors such as the change in temperature, humidity, and other environmental conditions can affect the sensor's performance in the way that controlled sightings may not replicate. And our study focused on specifically on ammonium nitrate as a premier PM2.5 composition, which limited the generalizabilities of our findings to other particles composition, which commonly found in different environments. And we use a limited number and the model of the sensors, which may restrict the applicabilities of our results to other sensor type or configurations, and expanding the study to expanding the studies to include a broader range of the sensors could provide a more comprehensive understanding. Besides, it is important to build a benchmark for how we measure the performance of our models. This helps all the local sensor applications meet the regulatory standards and are effective in real-world scenario. Looking ahead, we should expand our research to including various types of the sensors and test more kinds of the particles and conduct the field calibration to better simulate the real life scenario. And lastly, our findings support a purpose-driven approaches to selecting the calibration models. This means choosing the right model based on the specific environmental conditions we are studying and the results we have available. So in this study, random forest works best in high exposure settings, highlight the needed to choose model based on the specific monitoring needed. To conclude, these studies identified the random forest as an optimal calibration model for the occupational environment with high PM2.5 concentrations. Because among the model we test, random forest stand out due to its ability to manage complex nonlinear sensors behavior. This robustness makes it particularly suitable for the environment where PM2.5 concentration vary widely and can reach high levels. And our finding also supported the deployment of improved air quality monitoring solutions specifically based on occupational settings. By using random forest for calibration, we can enhance the accuracy and reliability of local sensor in this challenging environment, ultimately helping in better health risk assessment for our workers. And what can industrial hygienists use these studies practically? This slide summarized how you can do with that. Firstly, it can help enhance the calibration accuracy. Industrial hygienists can leverage the random forest model for more precise calibration of low-cost sensor, particularly in the environment with the high PM2.5 concentration. This improved accuracy ensuring the exposure level are accurately measured, which is essential for implement effective health and safety protocols. And then it helps with real-time monitoring. By applying these calibration techniques, industrial hygienists can support real-time monitoring of PM exposure, which enable improved decision making. And the real-time data is crucial in dynamic environment where PM levels may fluctuate rapidly, allowing for timely interventions, and allow for and it also helpful to improve the risk assessment. So with the more reliable exposure data, industrial hygienists can conduct more effective risk assessment, ensuring the compliance with regulatory standards. Besides, this data accuracy is especially valuable for the long-term health risk evaluation, helping the organization maintain the safer work environment. And finally, the workers' health, it help the workers' health protection. So adapting this optimized calibration methods, industrial hygienists can better safeguard the workers' health in industrial environment. And lastly, accurate exposure measurement allow for the better protective measures, contributing to overall workers' well-being and reducing the risk of the health issues associated with PM exposures. So in summary, this study provides industrial hygienists practical tools to enhance calibration accuracy, facilitate real-time monitoring, improve the risk assessment, and ultimately protect the workers' health. These applications demonstrate the values of robust calibration models in high-risk occupational settings. And that's all I have today. If you have any questions, please let me know.
Wonderful. Thank you so much for your presentation and sharing your research with us.
Thank you.
Yeah, to our audience at this time, we do have time for questions, so you're welcome to enter them into the Q&A. First question, more generally, what inspired you to do this kind of research? What made you interested in PM2.5 sensors and kind of inspired you to take on this research project?
First of all, one of my funding resource is like a local sensor related. It's make me like start doing the local sensor research. But when I'm doing that, I feel like we like really don't know a lot about that. We do not have a benchmark to give a definition like how accurate is accurate. Because I know a lot of people use that, but some of not calibrate that. Some of them like over calibrate that. I feel like the like serious research I did is like to build a benchmark, give like everyone an overview how we can handle the local sensor like in a balance.
Thank you so much for sharing. Another question came in. How are we to properly evaluate outdoor air pollution levels that exceed 1,000 UG per M3? In places like India, if the sensor break analysis falls below these measurements?
Like I said, when I doing that, the maximum I did is 1,000 microgram per meter. We need to if we want to measure the pollutant level exceed that level, we need to go further laboratory control the research to see how sensors respond like over that, because generally in America that not that high level exposure, so we didn't conduct any experiments over 1,000.
Thank you so much. Is there access to this random forest model, or how do you use it? Is this use only in association with the low-cost sensors?
So random forest algorithm is a machine learning things. I learned that from YouTube actually, and I actually from my research, my point is always that if we want to do like a daily life monitoring, like under 350, the linear regression is fine. But if you want to monitor the pollutant over that 350, you can use random forest or more complex models. I use R to run all these analyses. If you want to, I think if you want to learn more about the random forest or any other machine learning models, use YouTube or any online courses will be a good choice, but not necessary because daily life cannot have that much exposure.
Thank you so much. Another question, are there interference chemical particulates that should be considered that would alter the test results, such as those which absorb moisture or sublime at normal room or high temperatures?
That is a good question. We are going to doing that in our future studies. We think about that, but we did not do any tests yet.
Thank you so much. That was one of my other questions for you is what areas are you looking at continuing your studies, or do you follow-up studies you're looking to do?
Yeah, right.
Awesome. What do you see as the most effective strategy or policy for reducing PM2.5 levels? And how, on a global scale, and how do you see individuals contributing to these efforts?
I think on global scale, I think we really need to depend on the scenario we want to monitor. Because like I said, the local sensor can help with community-based can improve people's awareness of improve people's awareness. But I think make everyone have a accessible sensor in their home or like the working environment, make the workers get a wearable sensor with them. They can know the real-time exposure levels, I think, which is like the best way help them to reduce the PM2.5 exposure levels.
Thank you. Another question, was the calibration using a dust track or gravimetric measurement?
The dust track.
Dust tracked? Okay.
Yep.
And then they had to follow up, if the dust tracked, why not use gravimetric measurements?
Good point. That was the idea that follow the SOP with our chemistry department. I actually no idea why they did not doing that, but I will let them know. Yeah, to think about that.
Thank you for sharing. Awesome. And then I think that concludes the questions that we have from our audience. So thank you so much for participating, to our audience members. Thank you so much for sharing your research and your results with us. Do you have any closing thoughts or anything else you'd like to share before we end the webinar today?
That's all. Thank you.
Awesome. Well, thank you everybody for joining us. Be sure to check us out online for other upcoming webinars coming your way soon. And we're pleased to have you here today. Hope you have a great rest of your day.
Thank you. Bye-bye.